Well, let's go ahead and get started. Good evening, everybody. I'm Mike Conway, and I'm the VP of Programs here at the Arizona Geological Society. And this is our October meeting with Ramon Arrowsmith, talking about machine learning, robotic mapping, and particle dynamics for earthquake geology. Ramon, thank you for joining us tonight, and I'll leave it to you.
All right. Well, it's nice to see everyone tonight and to share our enthusiasm for geosciences. So before I get started on this talk, I just wanted to give a small advertisement for School of Earth and Space Exploration, because we are doing a lot of very exciting geology and geological sciences at ASU, even if we have a slightly different name. And so I just want to make sure everybody's aware of this. Sometimes people think, well, what happened to the geology at ASU? And it's going strong. And, we're training earth scientists with lots of breadth and rigor. We have field programs, writing intensive courses. We're trying to take things to be modern. So we're doing lots of digital field mapping, and you'll see the robotics that I'm going to talk about tonight. And we have all the degrees that you can imagine, including PhDs, astrophysics, exploration systems design, geological sciences, also masters in geological sciences. We have a BS in earth and space exploration, which is where our geological sciences degree is, if anyone's looking for it. We have a BA in earth and environmental studies, as well as a BS is coming. And then we have a partnership with the Mary Lou Fulton School of Education at ASU, and we have a bachelor's in secondary earth and space exploration. So just wanted to give that commercial, make sure everybody knows that we're going strong, and we're really excited to work with everyone. And if you're an employer, please keep your eye out for our students. So let's turn to the talk. So I'm going to talk about something I'm very excited about, and this has come from a relatively new collaboration with colleagues in CC, which is my other faculty colleague, Janeshwar Das, and we co-advise Xiang Chen, who's a PhD student. And so I want to give lots of credit to Xiang and JD for a lot of all the big ideas in here, and a lot of the work has been done by Xiang. So I don't want to make you guys think I've done all this, but as part of this collaboration, we've moved forward, and as you may know, always at the interface between different topics, sort of the interdisciplinary boundaries, is where a lot of exciting research is done, and that's something that I'm excited about with this project. So let's just move forward. So just big thanks to the group. You see Xiang on the upper right there. Also, Chelsea Scott and Daniel Laudavila took some of the imagery that we're going to discuss tonight. And then you see in the upper left there is JD's group and some of the collaborators here. And then in the lower left there is our stickers of all of our supporters. And this has largely been supported by California's Pacific Gas and Electric utility. They have a research arm that's been very interested in supporting this work for their seismic hazards work. It's also supported by National Science Foundation, Southern California Earthquake Center, and NASA. So what I want to, this is kind of the only real big slide or text heavy slide, but just to get some words out there. So documenting and interpreting the interaction between surface and tectonic processes for the records of earthquakes in the landscape is a central challenge for both fundamental understanding and application to hazard assessment. And so what is exciting is that advances in automation, scaling of data collection and data analysis for the earth sciences are evident, with increasing applications of robotics and artificial intelligence or machine learning. So what I'll talk about is a quick intro to robotics and AI, which is not really my expertise, but I'm learning. And then we'll talk about fault scarps with 2D rock traits constraining how they develop. And then we'll move into 3D, and we'll talk about fragile geologic features, especially precariously balanced rocks. And we'll talk about extracting them from the environment that we might measure, mapping, and then we'll look at the dynamics of them. And so the applications here are to earthquake geology, which is my expertise, but I think the potential is a lot broader. And so hopefully everybody here will think of things that are interesting to them, how this could be adapted. So one of the things I learned from JD is that the robots kind of really do the dirty, dull, and dangerous tasks for us. And so they can act as semi-autonomous sensor platforms. We can use them for sensor deployment and retrieval, and also data recovery and sensor health checks. And so I'm just showing some environments that might be dangerous, not necessarily very dull, and then also some robots, which are either airborne or ground-based in this case. So then also want to talk about, one of the things that I'm excited about is that robotics especially is a real gateway to STEM. So people love robots, especially young people. And so this is a way to pull more people into the geosciences and give them these modern skills. And so that's been exciting to me as a way to think about why this might be important from an educational standpoint. So this is a slide that JD put together that I think is really helpful, is to think about robotics and artificial intelligence on the same page as complementary uh, activities or processes. So robotics is the automation and scaling of data collection, while AI would be the automation and scaling of data analysis. And so robotics gives us this efficient collection of imagery or samples from hard to access places. It's less intrusive. We have all kinds of different platforms. And then AI allows us to efficiently analyze large volumes of data, go from data to information, and think of, idealization, sort of representation or traits of things we might care about. And we can use these tools of statistical machine learning, deep learning, to start to answer questions that are maybe presented by the data that the robots collect. So these tools have been used in or other areas, other domains for a long time. And also many science questions have helped drive the robotics and AI technology, but we think we can adapt these tools to many geoscience questions. So what do we mean by AI? Because this is something I was just learning about as a geoscientist. So it's artificial intelligence. It's widely used now for things like speech recognition, computer vision, autonomous navigation. It's really part of modern society. And so, but the ideas sort of developed starting in the 1950s, where AI is maybe the general term for machines capable of mimicking intelligent behavior. And then slightly narrower phrase is machine learning, which is a subset of AI where algorithms learn from data to make predictions or decisions. And then even more fine and more, as time has passed, deep learning has been developed, which is a subset of ML that employs multi-layered or deep neural networks. And so we've seen that all this has happened. It's really accelerating with the availability of computational power, data, tools, and know-how. And so tasks in geoscience include object-oriented image analysis, which is sort of what we'll talk about today, along with feature detection, also time series analysis and forecasting. And this has also been a real revolution in seismology. So if you look at seismology kind of earthquake catalogs, there may be 10 times as many events as were identified before, thanks to deployment of deep learning on seismic waveforms. And so some people might say, well, are geologists going to be absolute? And of course not. We still are needed, but we can use the tools of these machines to help us do our work. And so, how smart the machine can get depends on things like the quality and quantity of the input data, how well things are labeled, and also how we analyze them. So, but a machine can help. It can do things faster, more consistent, less biased, and maybe more thorough, and also do things that are boring to us. So let's just keep going here. So I want to give credit. This is something I was at a workshop last week, and Dr. Annika Braun was giving a little training about AI, and so I borrowed this from her. So we're going to talk about a few places. So let's just look at a map here. So we're on the lower right, that's Arizona, and we go to the coast on the Pacific Ocean on the left. And this is a topography along with active faults, and the redder it is, the faster the fault is slipping. So in Arizona, we have some black faults, which means they don't move very quickly, and a few blues and and greens, but when you get to California, see there's many more orange and red faults, which are the fast slipping faults like the San Andreas. So we're going to talk about places like Bora Peak, which is actually in Idaho. We'll talk a lot about the volcanic tablelands, which is where my cover photo was from. We will have an example from Arizona, which is the Granite Dells, just near Prescott. And then we'll talk a little bit about a site near the Diablo Canyon Nuclear Power Plant, which is on the coast of California, and it's what Pacific Gas and Electric owns. And so one of the reasons they supported our work was thinking about seismic hazards for Diablo Canyon. So let's first talk about fault scarps. And so one of the most famous, one of my favorite fault scarps was formed in 1983 by the magnitude 7.3 Bora Peak earthquake. And this map here, you see Utah, Arizona is the lower right, and we go up into Idaho. And so this earthquake occurred right in the Basin Range in Idaho. And it was really a famous earthquake. And so it broke the ground and taught us a lot of things about how normal faults work, but it also produced some spectacular fault scarps. And so you can see this one here, which formed in that earthquake. And so it breaks these alluvial fan materials. And so it's what we'd call transport limited. So the material's ready to move and be eroded and deposited at the base of the scarp. It just takes something to drive it, like, animal induced disturbances. The plants are sort of pushing things down the hill. Even rain splash can get things to move. So this is a kind of an end member fault scarp. And let's just zoom in. You see this person here standing at the base of the scarp. So the other kind of fault scarp is this one from Italy, where the fault is actually is exposed, the fault plane or the fault ribbon, and they say in Italian the nastrino, which is the ribbon of the recently exposed fault surface, which is right to the right of these people. The fault's coming out of the ground. So the fault scarp is a bedrock scarp. So those are two end member scarps. But what I'm really interested in is these rocky scarps. And so this is something we'd see in Arizona. It can be a fault scarp, or just could be any kind of a hill slope that might be formed. And I think it especially develops well in volcanic rocks that are highly fractured and also carbonates. And so we're going to look at these fault scarps, these rocky scarps that are from the Bishop Tuff in Eastern California. And so one paper we have published already from Zhang, and you see him on the right there working with the helicopter, the drone, and Devin Keating is helping him as well. So and then the second paper we're working on is hopefully will be published in Earth Surface Processes and Landforms. It's also led by Zhang. And so what you want to appreciate is these scarps are 20, 30 meters tall, but they're comprised of big blocks that are some proportion, like only a few times smaller than the scarp height, let's say. And so the way the scarp develops really depends on the motion of these big blocks. So here's the location in Eastern California. This big brown blob is the 760,000-year-old Bishop Tuff, which is an ignimbrite, and it's faulted by lots of faults that are in the Eastern California shear zone here. And so all these faults are, at least they were there before, but then the tuff was in place. And so then this distributed faulting has stretched and broken the Bishop Tuff as part of the transtension of the Eastern California shear zone. So this is a famous place. A lot of work has been done here to study the geomorphology, but also the faults. And so we went back to study them. And so we have a tiny little spot where we've worked. So let's look at this video from the drone just to see that fault scarp. So you want to look at all the blocks on the scarp. And remember, the left side is up and the right side's down. You see the vehicle there for scale. And you see the Sierra Nevadas are on the right. So we're flying to the south with the White Mountains on the left. And we're going to turn around in a moment. But what you want to appreciate is can we start to think about how these fault scarps work, how they form by the, faulting, and then the transport of the blocks on the scarp. So that's the real focus here. So we've got this diagram that you can see on the upper right. This is showing these these initially fractured volcanic rocks. So we know that this ignimbrite was emplaced and has these volcanic cooling columns that are the initial fracturing, but then they're broken by faulting. So the initial cooling columns are faulted, and so they are broken further by the tectonic processes. But then the third thing that happens is the blocks roll down the hill. They can impact each other, but also the 760,000-year-old tuff and the faults probably started slipping right then. So these scarps are about 700,000 years old. And so the particles are sitting out in the landscape for hundreds of thousands of years, heating and cooling. So there's also kind of a thermally driven fracturing that happens. So these three processes, volcanic cooling, tectonic faulting, and geomorphic fracturing, are kind of defining the particles that are on the fault scarp, their sizes and their orientations and their shapes. So these rocky scarps are not well defined by either alluvial or bedrock models. The challenge is to understand how the transportable material is produced and then how does it move. And so what we want to do is characterize these particles, which are the rocks. And so the breakthrough was when JD and Zhang said, well, let's just call it rock traits. Can we figure out the basic properties of each one of these particles, the most important one being the grain size as defined by the horizontal kind of cross section as we look straight down on it. But also we can then convert that cross-sectional area to the equivalent diameter for the grain size. But we can also look at the long and short axes of these particles to look at their eccentricity. Are they long and skinny? Are they more round in their cross section? And then also, can we look at the orientations of them? So here's what was done, again, led by Xiang and JD, is this pipeline here where we collect the data, we fly the drone, take a lot of pictures, and using photogrammetry or structure from motion, we can make a high resolution ortho map or aerial image along with the digital elevation models. And from that, then we can annotate or label a subset of the images or tiles of these images to sort of train and say, okay, this is a rock, this is a rock, this is a rock. And then the deep learning says, okay, given what you've taught me, I can calculate all the other rocks in the view. And so then it has to take some post-processing. There's a lot of cleanup on the input side and the exit side, but we get then a map of rocks, and then we can start to analyze them. And so the idea, this deep neural network architecture is called MASC RCNN. So that's the convolutional neural network. It's hard to say sometimes. These are some of the details about how it's implemented in this open source software. But the way you can think about it is just on the right, these kinds of image-based tools can identify things like people in a picture or an airplane. And it's the same thing. How do we know there's so many pictures of cats on the internet? It's this kind of approach, but this has been adapted for this scientific purpose. So the idea was to use these tools and put in the input data along with the training, and the input data included these RGB orthomosaic tiles, so little pieces, little pictures, little tiles of the ortho map, and then two different elevation data sets, so the color maps of the elevations and also the relative elevation. So those are put in, and then with the deep learning tools and the training, the output will be a map of the rocks. And there's one of the things that's done is you label a lot of the objects in sort of training, like a subset, maybe 10 or 20%, but you hold a few to the side as a test. And so we predict based off the training, we compare with the test, and we see what our prediction error is, which is quite low. So this seems to work. So here's the basic idea. So these tiles on the left are little pieces of the map, and then the output is these colored rocks. And so what's important is the colored rock means it's a unique color for each rock. So each rock is a semantically separated object. And so then we can start to do things like, well, what's the size of them? So the middle picture here shows the rocks color coded by their sizes. So the blue ones are big ones, the red ones are little ones. And then you can look at kind of the oblique view here. And then you can say, oh, let's look at the whole thing, 500-meter long fault scarp. We have a map of rocks. And so you can do things like, okay, so one of the things that we do is we maybe you remember from sedimentary geology classes, you can convert that diameter to what's called phi. So you take the minus log 2 of the phi. So you go from, a certain number of millimeters in diameter to a phi. And so in this case, these are big particles. So they're negative phis. And if you look at the histogram here, on the top, on the left, that's the distribution of all of the rocks. And so it's actually 230,000 rocks. So this is what's really exciting to me, because there's no way a person could map 230,000 rocks, but the AI can do it. And then once we have a map of 230,000 rocks, we can start to think about, well, what does it tell us about how these faults work, how these fault scarps develop? And so one of the key things to think about is a phi of minus 8.7, which is about the median grain size of the lower row is just the fault scarp itself, where there's 36,000 rocks. Since it's football season, American football season, that's about the size of the average or median rock size on these scarps. So about a football. The other thing that's useful, why the analogy with the American football is useful, is some of the rocks are, or most of the rocks are, if you look at the eccentricity, the middle column of the data, a 1 means that the long and short axis, if you divide one by the other, are basically close to the same, close to 1. So they're sort of more circular in cross section. But there are some of the particles that are more elongate, and so that would mean the eccentricity is like 0.5, which is kind of like what a football is. So so we get information about the shape of the particles, and then once we have the shapes, we can take the long axis and look at its orientation. And so that's what the right size polar histograms show, is just kind of what way all these rocks oriented. So here's just a view. You can see on the left is the grain size variation along the scarps, kind of median grain size for each little pixel. So you can say, well, that I know the scarp is there, but I can say, yeah, but look, you can see it in grain size space. And so if you look on the right, you remember we took a flight over it, and you can see, yeah, those are big rocks. Well, now I can tell you what their sizes are. So let's look a little bit more. This is one of my favorite outputs of this work. So what we did is, on the upper left, we took the fault scarp and we took the center line of the scarp and we kind of straightened out the scarp. So we just said, let's sort of move the particles around so that we can sort of align things so that the fault scarp is kind of straight or up and down. And then we could look at the distribution of things relative to the midline of the scarp. So the lower left, what it's showing is this east and west is just basically the center line of the fault scarp. And you say, well, west would be the downhill side and east is the uphill side. And so what you can see, this is like a quiz, which side has the bigger particles? And the answer is the uphill side. So that's why, and this is why it's a little bit of a test, is remember the grain size phi gets bigger going to the left, because remember it's the minus log 2 of the diameter. So this blue histogram in the back there is showing all those particles that are on the uphill side of the scarp. So what we're seeing is bigger blocks. And then on the west side, the downhill side, we're seeing a little bit of a spread and a little bit smaller particles. So then on the upper right is just a piece of the scarp. You see the box for it on the left, and all those red polygons are the tops of these rocks, or the cross-sectional view of them, I should say. And you see then this on the right side is superimposed the height. So you can see this black line is just a profile. So you get a sense the scarp's about 15 meters high here. But then on the bottom is kind of a cool diagram. So we take a distance perpendicular to the fault strike. So that's the distance kind of on upper plot there, horizontal distance, and then versus grain size. And then we kind of take these bins and we just look at, well, how many rocks are in each bin, and then what's the median grain size. And so what you can see, what's kind of cool, is that the largest particles are on the top of the scarp. And as we go down the scarp, they get smaller, and they kind of go into the background of what's on both sides of the fault scarp. And so we see the background sizes are sort of minus 6 phi, so they're smaller than American football. But as soon as we get to that scarp, we see these big particles exposed. And so a couple things then we can do, Zhang was able to do, is correlate like kind of scarp height or median grain size versus scarp height. So the taller the scarp, the overall the grain size is increasing. The sorting height with height. So the sorting uh, basically, actually it says this is sorting, but it's the standard deviation of the grain size distribution. So it actually means we're getting more particles of different sizes as the height gets higher. And then what's also interesting is that the mean grain size of the largest 10 rocks, which is shown here on the left, gets a little bit smaller. No, sorry, let's look at this. So as the phi gets larger in the negative sense, so minus 10.8 is a bigger rock. So as the scarp gets taller, the biggest rocks get bigger, which is kind of makes sense. So as we expose that scarp, we see these big volcanic cooling columns sort of popping out. And then also the small to large count ratio is also increasing. So again, we're getting more small particles as the scarp gets taller, but we also know that there are bigger particles at the top. So these data kind of give us some really interesting ways to explore these patterns of the distribution of grains on these fault scarps. So so this summary, I just want to kind of go back here. So this is the first part of my talk, and this is kind of where we got started. So it's the most mature part, but it's very exciting because it's basically gives us a chance to look at rocks on the ground surface, and to, in this case, we applied them to how fault scarps work, but we could use this for many other uh, problems that are associated with particles in geosciences. So that's kind of 2D as well, but we want to go to 3D. So one thing, just as a little bit of an aside, when I was preparing this talk, this tweet came out. This was an image from Mars, and these crazy precariously balanced rocks are on Mars. And so this, you see, it was from June 2022. So, you know, we might want to look at rocks, especially in 3D, because this is obviously a pretty fragile rock. And so this, as we transition into this 3D problem, I'm going to talk about the fragility of particles that might basically say if they're there, they haven't been shaken by any big earthquakes or affected by wind, anything like that. So, so the reason we want to do this, segmenting just means, can we pull these rocks out of their surroundings and work with them in a virtual sense? And so one thing that's been done over about the last 2 decades is to realize that we could look at rocks that are precariously balanced and use them as naturally negative indicators of earthquakes. So if it's there, it must not have been shaken enough to knock it over. And so we can look, for example, at the fragility, which is one way to measure it is if you look on the lower left, you go from the center of the rock straight down, the dashed line would be the gravity vector. So in other words, vertical. And then you look at the angle between that vertical line and the line to rocking points. And so the quiz would be, well, if you look at those two rocks on the lower left, which one's more fragile? Which one's more likely to fall over? And the answer is the left one, because it has a smaller angle, the alpha, which is a measure of that angle between the vertical and the rocking point. So you can knock it over a little bit easier. So we see on the upper right, that's a picture from Granite Dells near Prescott, one of our laboratories for these rocks. And so what has been typically done is to kind of pick one of these out and say, okay, we're going to study the heck out of it, because it's a really key record of not being knocked over. This on the left is from the Chiricahuas in southern Arizona. So it's not in granite, it's in volcanic rocks. But what I've wanted to do is say, well, let's take all of the rocks in the environment and look at their alphas, their fragilities. And so some will be more fragile than others. But the ones on, and so then on this diagram here on the right, you can see minimum contact angles. So the larger, as we go to the right, those are more stable rocks. And as we go to the left, those are the more fragile ones. And so P just means probability, or the number of them. And so what we want to do is look at the whole distribution, but we also want to especially look at, whoops, let me get the right color here. want to look at these guys on this end. They're the most fragile ones. But maybe we don't want to just look at one. We want to look at a bunch of them because we can get this ensemble can tell us about the history of shaking and the history of development of these features in a landscape. So that's been our goal, or that was the idea. And so then Xiang and JD said, oh, well, we can do this robotically. But the other thing is once we also want to understand the dynamics. So could you kind of put one of these in simulation and see what it would take to knock it over? Or could you, actually practically put it on some kind of table and shake it? And so there's some theory that's been done to pretend like it's a rectangle or a prism and knock it over. You can write the equations down for that. But obviously these aren't all rectangles or prisms. They're more complex shapes. And we have a collaboration with Christine Wittich, who's a professor of civil engineering at the University of Nebraska, and she's been helping us, kind of guiding us on some of this analysis. So let's look at it. So here's some of the questions we have about these features, these fragile geologic features or precariously balanced rocks. And so they include, how does the geologic setting of precariously balanced rocks affect its formation in the subsurface and exhumation to the surface? How does the PBR's geomorphic setting affect its emergence rate? Where in the landscape should we find these PBRs? What geologic and geomorphic factors control its slenderness, which is another word for kind of its fragility and ultimate failure? And how can we, by answering these questions, improve our confidence for using these as paleoseismometers? And so some of you may remember, but I had a PhD student named David Haddad who finished his work in 2012, but he worked a lot on the precariously balanced rocks in the granite dells, among other places. And we did have a Arizona Geological Survey report that he produced. So maybe some people saw that. So now with the collaboration with JD and Xiang, the idea is, well, let's see if we could get a bunch of these rocks, but in 3D. So we start with the same approach as before. So we fly the drone, we make a map, we produce these orthomosaics, and then this 2D rock detection is exactly what we just did on that fault scarp. We get the georeference bounding boxes, but then we take the point clouds. So these landscapes in this structure from motion or photogrammetry tool are actually made of a whole bunch of points that represent uh, locations on the ground surface where there was good correlation from multiple images. And so that represents a point. And that's kind of the fundamental data. And so once we have the 2D view of where they are, we can make a 3D box that contains the rock and cut them out, and we have 3D rocks. And so this is just kind of walking through it. Here's the vertical view. There's the detection in 2D. There's again, the sort of georeferencing, boom. Now we've cut these rocks out in 3D, and there we have a rock. And so the points, again, that's that point cloud. That's one of the outputs from this photogrammetry. But now the work of Xiang has been to separate it from its surrounding, its pedestal. And so here they all are. So this is, to me, is really amazing because suddenly we have a bunch of rocks. And so you could do all kinds of things with them. But right now, what we're trying to do is get their slenderness. So get the alpha, but even easier than getting the alpha, that rocking angle, we can just get their height to width ratio, because obviously a taller object is going to be more fragile rather than a short one. So, and so what has come up is well, what I just talked about is something that Xiang calls the off-board method. So I took all these pictures, that we made the calculation of the orthomosaics and the point clouds in the office, and then I just gave him the data, and then he extracted these rocks. So it's nice, works right now. But what if we wanted to do this more robotically, so in real time? Because that off-board approach may take too much. It's not necessarily efficient. It's kind of brute force solution, and we don't always get all the information about the basal contact, which is really where a lot of sensitivity to the ground motions is recorded. So then the onboard method is to do it with the flying robot, basically, and so that means we can sort of in real time, the robot can say, okay, I need to go look and get a good view of the base of that rock, and then also make decisions, where are all the rocks in the landscape, and try to collect more targeted data. And so here is one of the robots. This one's called Rocky 2, and we're working on building Rocky 3. But you can see this one has it has two computers. So it has one computer that's the brains to fly it, but there's a second computer, this NVIDIA TX2, which is the one that does the detection. And then it has a couple of different cameras that do the real-time mapping. And so, this offboard method is basically separating the robot or the drone from the computations, whereas the onboard puts the brain on the drone. And so here's just a view, Xiang working on fault scarps in Northern California with Rocky 2. And so here the idea is set the robot out, set it's a hexacopter. One of you guys should mute. I think that's David Briggs. You need to mute because I can hear your someone in your background. So the idea is send the drone out. It makes a kind of a lawnmower search pattern, and it's flying along. And then let's say it's like, oh wow, I detected a PBR. So using the same approach that we've just talked about, but in real time. And so it sees that PBR and starting to get some points that are defining the PBR. And so then it verifies that it's there and it says, yep, that's a PBR. So it switches into a new flight mode and it flies a conical flight around the rock. And in our Rocky 3, it would have a LiDAR on, so it laser scanned the rock, including its base, and then it flies on to the next one. But in the meantime, we get this really nice, like in real time product, which is 3D model of the rock. And so this is really the goal that we're working toward, but I'm really quite excited about it. So finally, you might say, okay, well, that's fine, but what are you going to do once you have all these rocks? And so the answer is we, meaning mostly Xiang, but with our team all together, have built this thing called the virtual shake robot. So this is all in the virtual environment, doesn't exist physically. But what he's been able to do is pull together 3 different sets of software. So the first is called Gazebo, which is the simulation or modeling environment that basically contains all of this activity. Then there's ROS, which is the robot operating system, which is where we control and monitor everything in the environment. And then the other big thing is to use the physics engine called Bullet. And this is basically does the physics of rigid body interaction between particles. And so what he's built then in this environment is this robot, which has a base, which is kind of the blue thing, the motor. Remember, it's all in the computer in Gazebo. And then he built this big pedestal, which is a 50-meter or slightly less than 50-meter kind of block of rock. And then we can place the little PBR on top of it. So that's pretty cool. We can use that for the basic experiments. But the other thing that's amazing we can do is drop an entire outcrop onto the virtual shake robot. And so that's what's in the upper right here is, I'll show you this place in a minute. This is called Double Rock. It's about 30 or 40 meters long and 20 meters high. And then on the lower view, that's one of the outcrops from the granite delt. So we can put that onto the shake robot and then shake it. And so here we're using these tools, the sort of particle dynamics. So we use these modern physics engines to simulate the toppling of thousands of rocks. We use these high resolution 3D digital terrain models to set up the environments, and we can carry out many simulations to explore the behavior of these complex objects. And so what it does is it gives us both the fragility, like the instantaneous, did it fall over or not, as well as what we call the large displacements, or how does it fall? Where does it end up? The fate of the particles. And so these physics engines are really coming from the gaming industry where, these days everybody wants to have realistic games, video games. So you might as well just do the physics correctly to begin with. And so the idea is to pull those physics tools out and use them for science. So on the lower right here, I've just showed a video Xiang made of simple prisms and cylinders on this little substrate, and you shake it a little bit and you see that they might or might not fall over. Let's just watch one more time. Boom, we put a little shake in there and some of them fall. So we specify the inertia, so basically the density and the size of the object. We can also specify the surface, the friction. So these are kind of high friction contacts, so it doesn't slide, but it actually topples. So here's the basic idea of the shake robot. And so then this flow chart is to basically explore in a more large parameter space. If you shake it at a different set of accelerations and velocities, can we look at what the overall stability of an object is? And so this is what this video shows. So the left side is this poor idealized little rectangular cylinder that's being punished by being shaken. But on the upper right, what you see is the vertical axis is peak ground velocity divided by peak ground acceleration, and the horizontal axis is peak ground acceleration. So this is the kind of standard way to describe the fragility of an object, because it's not just, did you shake it, but it's kind of what was the velocity, how long was it being shaken. And so all these dots, if they're blue, that means it stayed up, whereas if it's red, it fell over. And so Zhang was able to build a kind of simulation environment to do these calculations in Gazebo. And so here they are again, and he did it not just for one rock, but for many rocks and with different orientations of the initial shaking. And this is just with a simple sinusoidal pulse of motion, kind of 1 meter per second per second. But it's possible to put in a realistic seismogram as well, which he has done. So let's go to California. This is the California coast in the central part of the coast near San Luis Obispo, and it's near to the Diablo Canyon nuclear power plant. And so what you can see, what's important to appreciate is this surface right here is the 100,000-year-old marine terrace. And on that terrace is this really pretty paleo sea stack. And on that sea stack is a precariously balanced rock, this one right here. And so this is called Double Rock. And so we went there with our team, and the PG&E colleagues supervised us, and we wanted to study this particular precariously balanced rock and see if we could understand its dynamics a little bit more. So we flew the Rocky, sorry, there we go. We flew Rocky 2 there, and we also flew our other drone. Here's just another view. You see that PBR, this one right here. There's some other ones, but this is the one that's kind of the most famous. And so let's look at it. So here it is. Basically, oh, sorry, it was already playing. Here we go. So here it is. And what Zhang has done is took the PBR off the outcrop virtually, put it on the virtual shake robot, and now he's shaking it. And so we have this fragility distribution, the PGV over PGA versus PGA plot. And we see that it has a certain fragility. But then what he did, here's the poor thing is getting really worked on, is he had 12 different sort of experiments running at once. And so, sorry, let me just go back because I want to finish talk about this. So this one is basically what we would call the anisotropy. So if you shake it with different directions relative to the shape of the PBR, you could characterize the fragility with different initial ground motion directions. And so then the other thing he did while he was at it was to this is what the other part of this video will show, is the large displacement. So let's take that object and see here, it's not on the outcrop yet. Oh, there it is. So he's put it in. And now on the right, you can see the incoming ground motion is shaking that outcrop a little bit. And this is kind of weak motions. This would be like an earthquake that was a little bit further away. Oh, here's a bigger earthquake. Oh my gosh. Woo, doof, doof, and it falls. And so you might say, oh, it's kind of silly, but it's totally realistic. It's real ground motions, real physics, real particle interactions of this little precariously balanced rock. And so here we're putting in a real seismogram. So that's what that curve is on the left, is time and displacement. And you can see that we shake it. And so what's important also you get a sense of is the context. So if the PBR is sitting by itself on the virtual shake robot on a flat surface, it's going to fall over pretty much in every direction. But here it's kind of in this niche. And so the first ground motions that maybe push it into the niche keep it from falling over, whereas we might need a stronger ground motion in the direction towards the or away from the main outcrop. And that's something that's been actually quite interesting to our sponsors, to PG&E, given that context. So here he is showing it without the lateral support. So this was kind of a thorough review of that. I'm just going to keep going. So here's just a summary. So this was 2 different directions, 180 degrees different from the first motion, and a little bit of difference of fragility. And you can easily knock it over. Sometimes you see how in the red zone, there's a little bit of blue. That means it was kind of perfectly balanced. So it was falling, but then the shake robot pulled it back just in time. Here's the real ground motion with it falling over. And there's the large displacements with, these are just the kind of stills of that video. And you can see on the right is the trajectory. So way that particle fell. So what I am excited about is we're working on the fragility right at that location. The fact that it's still there means that it hasn't experienced a certain set of peak ground velocity or peak ground accelerations, but the trajectory takes it down to the ground. But what I want to draw your attention to is all these other particles right here, which have already fallen. And so could we do this in a reverse sense and put these guys back up to where they came and kind of look at, well, what did it take to knock them down? And so this is the real power of this virtual simulation environment, is we can do hundreds and thousands of calculations and kind of experiment. What does it take to knock it down? Where do they end up? And so this is kind of where we're heading with this. So let me just see, we're almost done, guys. Oops, sorry, when I annotate, then I lose the chance to advance the screen. So, okay, here we go. And so here's just a couple of PBRs from Granite Dells. There's 3 of them now, and they, we just took that environment and pushed it 2 meters to the left in 1 second. So we just poof. And so, actually what happens is the rocks didn't move, but the ground did. And so once the ground moved out of the way, then they fell. And so you see A0, B0, C0 ends up at B1, A1, and C1. And so we get this interesting trajectory of the ground motions. So we can, or trajectory of the particle motions due to the ground motions. So what's exciting here is we can, again, explore what does it take to get these guys to move. If we find some at the bottom of the hill, can we think about where they came from? But you can also imagine this is huge utility for hazards. And so there's some interest from PG&E to look at some of their dams and penstocks, which are below slopes, and can we calculate the hazard posed by those hill slopes from particles up on the hillside. So that's the end of my story. Just to summarize, these applications are for these earthquake geology problems, which are interesting to me, but I think the potential is a lot broader. So other things to do are to do this extraction, identification, and pulling these objects out at scale. So 230,000 particles in 2D is not bad, but can we do more, a million? And then doing it in 3D is trickier, quite a bit harder. And then can we do the extraction in dense areas? So now if the PBR is kind of by itself, we can extract it. But if they're sitting on top of each other, it's going to be a lot harder. We need to continue to enhance our understanding of the bottom of the 3D particles to look at their fragility, because that's the contact geometry is really critical. We want to validate these physics tools, the physics engine, with more tests to make sure we can trust it. And we want to add more complexity to the rheology and material properties. So what that means is when the rock falls, could it break, for example? Right now it's hard, it just falls and that's it, and it bounces. But could it fall and lose some of its energy by kind of plastic deformation of the soil? So that needs to be implemented. And then can we apply these physics tools at scale to look at landscape evolution, like use the physics tools to calculate the particle motion on the fault scarp? And then refine results for probabilistic seismic hazard assessment, because in the end, our sponsors want to know what's the hazard. Can we improve the understanding, decrease uncertainty for the hazards for something like a nuclear power plant? And then what I've talked to you mostly is just about the geometry, but the ages of things is actually the really hard part. And this Surej, this was from, I gave a talk at a laboratory in France where they have a big cosmogenic dating facility where they could date some of these rocks. And so that remains to be the biggest challenge is how to figure out how long it's been in the landscape. So one of the things we've worked on here is to try to look at particles that are sitting on glacially polished surfaces, because we know they were in place like 15,000 years ago when the glaciers were advancing in the Sierra Nevadas. The glaciers pull back and they leave the particles. So anyway, lots to do, and I'm done. So let me stop there and take some questions.
Ramon, that was great. That was really cool, but I do feel obsolete.
No, don't feel obsolete. Just think of, it's just like, it's a better tool. It's a better screwdriver. Just a much better screwdriver or a fancy drill, maybe.
Yeah, exactly.
But it's part of our toolkit.
No, that was spectacular. Now, if I remember those faults in the volcanic tablelands, they kind of ramp out of no place and then they ramp back down into it. Do you see things along the edges that tell you something about the way that these faults are behaving?
Some. I mean, we haven't really explored that as much as we'd like to. That would be next. So right now we've just studied the one fault, Scarp, which is 500 meters long, but there are tens of faults in the volcanic tableland, and that's what was studied by other people, is this kind of slip versus length question, and this kind of elliptical distribution. So I would like to do that in a future study now that the tools are built, is to go back and collect these data on many more fault scarps. So we could really do some application now that the tools are maturing.
Okay, very good. Other questions? If you'd like to unmute yourself and ask a question, please do so. I don't see anything in the chat unless something just came up.
There's one. So somebody asked, have we tried SSD, single short detector, to detect grains or blocks? I actually don't know what is single short detector. Is it a kind of a machine learning? Let me just look it up really quick. Single shot detector. Oh, single shot to detect multiple images. We haven't used it. I see that it's part of the computer vision toolkit, but we haven't. And that would be something probably JD or Zan could speak a little bit more to.
Mm-hmm.
And I see JD's here, so if you want to say anything, JD, go ahead. But thank you for all that you have done.
Yeah, hi Ramon, great talk. I can just chime in. We have been using faster RCNN kind of lineage, so mask RCNN, but definitely we should compare with the other SSD detectors and see how we do. And in our case, we are doing segmentation and kind of instantation. So each object is a separate thing. So we often choose our networks based on those requirements. Can we segment and split the objects? Thanks.
Thank you very much.
Mm-hmm.
Some other questions? We still have a few minutes. Anybody? I tried to push fast through the talk, so even if there was something unclear, anybody wants me to show a slide again, or
I wish I could think of some great questions to ask you, Ramon, but this was all very new to me. But it seems really exciting, and there must be a number of other folks doing some of the same things at other institutions. Are you working with a whole lot of people across the globe?
Not so much. I think, this problem of what they call granulometry or measuring particles is starting to be, I mean, it's always been there for sedimentary geology, but using these next generation tools to look at particles like sedimentary rocks is coming online. But I haven't seen anybody do it in this way with the real heavy duty deep learning implementation. There are other kind of image-based classifications, people segmenting the particles, but this one seems particularly special because of its real reliance on the deep learning. And then, Mike Doe, go ahead, please.
Yeah. I guess this week, Glenwood Canyon here in Colorado, they're actually shutting down the interstate for long periods of time because they've got large rocks that peel off and crash down on the elevated sections of I-70 that goes through the canyon. Do you know if they're using this technique or something similar to it for road canyon, slope stability or slope hazards?
Not exactly. I mean, the problem with slope stability is a big one, and I know this kind of amazing pictures you see on the news when those particles, those boulders come down to the road. Um, so we have seen, for example, papers published using Bullet for 3D, like it's like 3D Monte Carlo modeling. So they get like a 3D volume of where the particles are most likely to go. So they run this model many times with small perturbations, and you kind of get a sense of the hazard. So that's been done, but not widely, and it's definitely not used in production as far as I can see by like departments of transportation. But we did talk with some of the California colleagues, both PG&E and California Geological Survey, and they were interested at looking at some of these rocky outcrops. Like if you have a bunch of rocks kind of sitting on a slope that look kind of unstable, can we go up, image them and segment them, kind of define their 3D geometry, and then turn the virtual shake robot loose and then look at where they go. So you could forecast, I think, reasonably accurately where they ought to end up. And that would be an obvious hazard tool.
And I have one more question. The Bishop Tuff seems to have an integral fracture pattern already in it. There's the way it cooled had these incipient fractures that are already present. And then when the graben formed, it sort of fed off of those pre-existing fractures and stuff. How does it work when you don't have, let's say, just bedded, some sort of other bedded form like a quartzite or a sandstone?
It would still work, actually. Be kind of interesting to compare. To me, what's neat is it's a little bit serendipity. We just had these really beautiful data from the volcanic tableland, and we started talking about them as our collaboration started. But it's interesting because you start out with these big columns and they have a certain diameter, let's say, and then certain fractures that bound them, and then a horizontal distribution of fractures that sort of define these big blocks. But then we fault that fractured rock mass by the tectonic faults. And so those particles will kind of roll against each other, and they kind of get ground down in the fault zones. They might break, into a couple pieces, and then go, then geomorphically collide and otherwise fail in the hundreds of thousands of years of thermal cycling. So these same kinds of processes would operate on any rock. I just think that if you broke a quartzite, you might break it for the first time with the faulting, or some larger wavelength tectonic jointing to begin with. So I'm interested, that'd be even further down the road, would be to use these tools on scarps developed in different kinds of rock and see if we could tell, the signature from the particle distribution.
Mm-hmm. Ramon, there's several comments in the chat now.
That's right. So so JD's helping. Thanks, JD. Dale asked, what's the smallest particle? It depends on the resolution of the imagery, but right now our smallest particles are just a couple centimeters in the study on the fault scarp. But yeah, it just depends on, you need a couple pixels minimum to define the particles. So it depends. And then JD's also answering for Ganesh Krishna, who is asking another bit about the machine learning and kind of how you look at the sensitivity to the input versus output in the machine learning. So some good technical answers there. So yeah, we're just at the bottom of the hour. So people should feel free to contact us if you have questions. But thanks for the opportunity to share this with you. And hopefully there was something interesting in there for everyone.
Ramon, thank you so much for doing this. And for everyone, Ramon has given us permission to record this, so we'll post this up at the Arizona Geological Survey's YouTube channel, and we'll inform the scientific community here in Arizona and elsewhere that it's there and people can look at it.
Yeah.
Sir Ramon, this is Ganesh Krishnan. First of all, thank you for this presentation. This is amazing, amazing work by JD and Zhang. Hats off to you guys. I just wanted to see where do you guys have any opportunities in terms of research and all that, because I have a background in artificial intelligence, and I'd love to assist in any future work that you guys have, and how can I contact you guys? That was my question.
Well, it's a great question, and yeah, we have a big group, but yeah, it'd be great to get to know you better and see about how we might collaborate a little bit. So what I'll do is let me just put my email address in the chat. Where did it go? Here it is.
Yes,
Yes.
Ramon, thank you so much for doing this. Unless there are any last questions, I guess we should let you go and make what you can of the rest of your Tuesday evening.
Yep. Well, thanks again for your interest, and good to see everybody and share our enthusiasm for geology here in Arizona.
Yeah. Thanks a lot, Ramon. Bye-bye,
Bye-bye.
everybody.
Thank you.